Decentralized networks operate on a paradox. Blockchains require radical transparency, so nodes can verify that transactions are valid, but proprietary artificial intelligence models require strict data confidentiality to function and protect their underlying logic. When user data and model weights are executed in plain text on a public mempool, the network can verify the math, but the intellectual property of the model and the user's private information are immediately exposed to any observer. To bypass this exposure, the industry relies on two workarounds. Zero-knowledge proofs, or ZKPs, are cryptographic protocols that allow a party to prove a statement is true without revealing the data that proves it. tEEs are secure, hardware-isolated areas within a computer processor that execute code in an environment invisible to the rest of the system. ZKPs have a structural limitation in this context. While they can verify that a computation was performed correctly, they cannot compute over hidden data that is sourced from multiple parties. tEEs can compute over hidden data, but they require the network to rely on centralized hardware trust. This means the security of the decentralized system is tied to the physical integrity of a chip produced by a single manufacturer. This hardware reliance creates a specific risk. If the hardware enclave fails or restarts, the localized private keys it uses to secure data are lost, and the state of the computation cannot be recovered. Unless a decentralized network can compute over hidden data without a centralized hardware point of failure, on-chain AI agents cannot remain secure and trustless. Fairblock's target for this architecture is the Unruggable AI trading agent, an autonomous entity that executes DeFi strategies using proprietary data. This agent operates without exposing its internal model weights to the network, and without exposing the user's input data to the model's creator. To achieve this, the system must perform mathematical operations directly on encrypted data, removing the need for plain text exposure at any point in the cycle. The primitive that enables this is threshold Fully Homomorphic Encryption, or tFHE. Fully Homomorphic Encryption is a form of encryption that allows computation to be performed on ciphertext, generating an encrypted result that matches the result of operations performed on plaintext. By utilizing tFHE, Fairblock changes the blockchain from a passive ledger into an active engine for confidential computing. AI inference follows a standard equation. User inputs, X, are processed through proprietary model weights, W, to generate output, Y. In Fairblock's system, an encryption function is applied to both user inputs and model weights before they are ingested by the network. Fully homomorphic encryption preserves the underlying mathematical structure, while data remains opaque. The network performs matrix multiplications directly over these ciphertext blocks. The computation happens without decrypting data in RAM, producing a new block of static noise representing the encrypted trading decision. This final output remains strictly encrypted. Because the inference happens on ciphertext, the model owner never sees the user's input data, and the user cannot extract the model's weights. This solve for data exposure creates a new challenge. The network must now manage who controls the decryption key for that final output without reintroducing a central point of failure. If one entity controls the master decryption key for the encrypted output, the AI agent is vulnerable to censorship. That single entity could withhold the key to prevent the agent from executing a trade. Fairblock addresses this through FairyRing, a Cosmos SDK-based app chain designed for decentralized key management. FairyRing utilizes multi-party computation, or MPC, distributing computation across multiple parties so no individual sees others' data. In this architecture, the master decryption key never exists entirely on any single network server. The final decryption key can only be derived when a specific threshold of these independent validators cooperate to combine their fragments. By fracturing the key through MPC, the agent's autonomy is tied to decentralized network consensus rather than a single corporate actor. FairyRing employs conditional decryption. The network will only reconstruct the key fragments when predetermined on-chain conditions are met. These triggers are hard-coded into the protocol, like a specific block height, a price threshold, or a verified vote. This mechanism of conditional decryption provides a solution for catastrophic failure risk of standalone tEEs. While tEEs are highly efficient for secure enclave computing, they face a fatal flaw. They lose their localized private keys during a system crash. Fairblock's MPC network acts as a decentralized, trustless backup for these enclaves. The network monitors the blockchain to validate the tEE failure state. When the failure condition is confirmed, the validators collectively decrypt a recovery key to restore the agent's state. This conditional recovery mechanism enables the AI agent to survive physical hardware failures without a centralized corporate backup. By separating computation from data exposure, Fairblock changes the economic incentives for on-chain AI. It enables secure data marketplaces where users can monetize high-quality information for model training. Because tFHE ensures raw data is never exposed to the buyer, providers can sell access to their information without losing control of the data itself. For model creators, this means proprietary machine learning can be used for risk assessment or trading intents without leaking intellectual property to the users. This architecture makes proprietary datasets viable for decentralized markets, removing the trade-off between trust and confidentiality. The final step involves routing the conditionally decrypted output cross-chain via an IBC relayer. IBC, or inter-blockchain communication, is a protocol that allows different blockchains to transfer data and value between each other. This allows the AI agent to execute its trade on a target DeFi protocol autonomously once the encryption is lifted. Fairblock's synthesis of tFHE for ciphertext computation and MPC for conditional decryption creates a framework for Web3 AI supply chains. This system protects user data, preserves model sovereignty, and ensures execution autonomy without relying on centralized hardware manufacturers. Making confidentiality programmable allows decentralized applications to function with the same privacy guarantees as private databases.